Well, welcome everyone. How's everyone doing this morning? Good? So welcome to modular Java or modular architecture today. So what we're going to spend some time talking about here over the course of the next few hours is how do we develop software systems with a modular architecture. And hopefully, over the course of that 3-hour period, my voice will hold out for me. This information is based upon the material that was published in my book back in March. The book title is Java Application Architecture, Modularity Patterns with Examples Using OSGi. So today when we walk through some of the code that you see here, know that all of the code that we demo here is available on my GitHub repository. There is the URL for that code. You can also just Google Prag Kirk GitHub and that should take you to it. So you'll see 3 different projects there if you do go to that GitHub repo. And we're going to be walking through a certain amount of code from each of those individual projects. So my goals today are actually pretty simple. To help us start designing modular software system when we get back to work next week. And for those of us who are leveraging Java as our platform, is to not necessarily flip the bit on OSGi as too complex. Now, I don't come here today to talk a lot about OSGi. I come here today to talk more about modularity and how we design software systems with a modular architecture. Towards the end of this session today, I am going to spend a little bit of time showing you how easy it is once we have a system that's been designed using a modular architecture to take that and OSGiify it, that is, bring it under the control of OSGi. And we're going to see this from a number of different perspectives. Probably the most relevant perspective is how do I develop a web application that has a modular architecture and then something that I can bring under the control of OSGi, and to really see the differences, the advantages of a modular architecture as well as the advantages of OSGi. So we're going to start out introducing modularity. What is it? What are the benefits of modularity? Then I'm going to talk a little bit about the modularity patterns. These are 18 patterns that were published in my book and how they help us go about designing a system with a modular architecture. Then we're going to take a subset of these patterns, not all of them, but we're going to take a subset of these patterns and refactor an existing web application that's been developed with a relatively monolithic architecture, similar, I suspect, to what a lot of us have been doing over the course of the past 10 or 15 years, and we're going to refactor this to an architecture that is very, very modular in nature. Once we've done that, we're going to take that exact same system and with just 2 or 3 relatively small modifications, we're going to introduce OSGi into the mix and show some of the runtime benefits of modularity. Actually, we're going to do that after we introduce OSGi briefly. So that's our agenda today. We've got 3 hours. We shouldn't have a problem getting through the material unless I get too long-winded. Hopefully, at some point, maybe 75 minutes in, we'll take a short break, let everyone go get something to drink, use the restrooms, whatnot. So let's get started, introducing modularity. What are the benefits? Why is modularity a necessary component of agile architecture? On Wednesday, I'm going to talk about this idea of architecture all the way down. We're going to explore that briefly here today. And then what challenges face us? Well, one thing is for certain, modularity is absolutely not a new concept. It was initially introduced in software engineering in roughly 1972 in a paper written by David Parnas called On the Criteria to be Used in Decomposing Systems into Modules. And in that paper, Mr. Parnas talks about how when we modularize software, some of the benefits include extensibility, maintainability, the ease with which we can understand the software system, so on and so forth. But what he didn't discuss in that paper is a concrete definition of a software module. And I believe that this is one of the challenges that we have in software, is that there are certain terms that we use relatively loosely that kind of assume their own meaning within the minds of the beholder. A really good example of one of these terms is software architecture. I would wager to say that if I went to 10 different folks in this room and asked them what their definition of software architecture was, it's likely that I would get 10 different answers. Now, each of those answers may have common themes associated with them, but it seems that we each have our own idea of what is meant by software architecture. The same with module. What is a software module? Well, on the Java platform, over the past several years, we've brought a great deal of concision to the definition of a software module. And what exactly does that mean? Well, quite frankly, whether we're looking at the Java platform, Java SE, we're looking at module frameworks, whatnot, a module on the Java platform is quite simply a jar file. Now, that might not seem very exciting to many of us, but I hope that as we walk through the remainder of the session today, you'll see some of the interesting things that we can do with modularity to really bring a great deal of extensibility, maintainability, increase the understanding of our software systems by focusing on modularity. In addition to that, a module system, some of you have probably heard of OSGi. I'm sure that some of you have probably been following the trials and tribulations of the Jigsaw module project associated with the OpenJDK. Whether you're looking at OSGi or Jigsaw, both define the unit of modularity as a jar file. What are some of the benefits here? Briefly, a unit of reuse. Think about how we go about reusing software systems. In fact, if you look historically back at one of the main benefits touted of object-oriented programming, one of its main benefits was reuse. Well, I think over the course of the past 15 years or so, we've realized that the object-oriented paradigm does not lend itself well to this idea of reusability. And that's because objects typically exist at the wrong level of granularity to achieve a great deal of reuse. Modules, on the other hand, are an ideal candidate for reuse, as stated by the reuse-release equivalence principle. The unit of reuse is the unit of release. In order to make something reusable, I have to make it releasable. We're going to talk a little bit more about that as well. So, definition of a module, a jar file on the Java platform. A module system provides a runtime environment for modules. What does that mean? What does it mean that a module system provides a runtime environment for modules? Essentially what it means is it treats the jar file as a first-class citizen on the Java platform. And we're going to, again, see some examples of that a little bit later. This brings us to the different facets of modularity. Think in terms of the object-oriented paradigm and some of the challenges that we've encountered over the past decade or more in trying to apply the paradigm's practices. It was relatively easy to understand how to use the extends keyword or the implements keyword, i.e. the programming model. That was relatively easy to do. It was relatively easy to understand how dynamic binding worked, how if I bound to an abstract class, I could substitute an implementation at runtime. So we can draw an analogy between the object-oriented paradigm and modularity to a certain extent, in that the various keywords that allow us to implement object-oriented constructs are essentially the programming model surrounding the OO paradigm. From an infrastructure standpoint, the runtime standpoint, it's the dynamic binding that takes place as we run our systems. But there's also this design paradigm. How do we go about designing good object-oriented software? And I believe in the early 90s, as many of us, early to mid 90s, as many of us began using the OO paradigm, what we quickly discovered was that we understood dynamic binding. We understood how to use the syntax and semantics of the various languages. But what often challenged us most was how we go about designing good object-oriented software. The design paradigm, the techniques that we use to design good software. You can find similar examples of that over the course of the development of the last 10 years or so. Let's take a look at EJB, for instance. I remember the very first project that I went on. A lot of you will probably chuckle at this. The very first project I was part of, where they decided they wanted to use enterprise Java beans. This was probably 8 years ago or so, maybe a little longer. And what was interesting was that as I got there and I looked at this system, they had approximately 100 EJB, entity beans. And basically, they had an entity bean for every domain object in the system. Now, the programming model surrounding EJB was relatively straightforward. The infrastructure, the specification was relatively easy to understand. It wasn't an issue of getting these EJB to run in the environment. The real issue was that the design was seriously flawed to have that many entity beans associated with the software system. And so when we think in terms of modularity, we see many similar themes associated with modularity in that there's the design paradigm. How do we go about designing good software modules? We can do that on the Java platform today. We have everything that we need to design modular software on the Java platform today. The programming model and the infrastructure, the runtime, is a product of the framework that we will eventually use that brings modularity, that treats modularity as a first-class concept on the platform. That is, OSGi or Jigsaw, or perhaps something else will emerge. But even using a module framework does not guarantee to any stretch of the imagination that we are going to have a well-designed modular software architecture, because the design paradigm is still there. We still have to design the system. What's the right granularity for a module? How much should it do? How behaviorally rich should a module be? What's the right weight for a module? A lightweight module, heavyweight modules. One of the benefits of a lightweight module, of course, is that it's going to be easier to reuse across a variety of different contexts. However, the disadvantage of a lightweight module is that because we reuse it across a variety of different contexts, it is inherently going to be more difficult for us to use. That is, we're going to have to configure it to our environment each time we want to use it. This is what I like to typically refer to as the reuse-use paradox, or the use-reuse paradox. As you increase the reusability of a piece of software, you inherently decrease the usability of that piece of software. There are other interesting paradoxes surrounding software development that I oftentimes don't think we give a lot of conscious thought to. Let's take a step back here for a minute. What is the goal of software architecture? Why do we spend time, energy, and resources on software architecture? Well, one of the reasons, probably the obvious reason, is that we want to design a system that is flexible, that can adapt to change over time. How do we do that? We do that by trying to design flexible software systems. We do that by leveraging design patterns, so on and so forth, other techniques that we've employed. As we design these more flexible systems to try to take advantage of reuse so that our systems are extensible, that we have lightweight entities that are highly reusable, that we can configure to context, so on and so forth, the natural byproduct of that flexibility is that we increase the complexity. And here we can see a quote by Ralph Johnson in an article that was written by Martin Fowler titled, "Who Needs an Architect?" Making everything easy to change makes the entire system very complex. So ultimately what we find in many situations is that the flexibility that we put in place to try to create a system that is adaptable results in an increase in complexity that ultimately decreases the survivability of our software system. In fact, we achieve the exact opposite of what we tried setting out to achieve. That's not to say that we shouldn't strive to develop flexible software systems. That's not at all what I'm saying. What I am saying, however, is that we need to identify the areas of our system where we need this flexibility. Where do we need the flexibility that is going to bring this natural increase in complexity with it? So if I have this software system, whether these be a class diagram, whatnot, assume they're classes for this example. And if I had a system that only had this few classes in it, obviously it would be a pretty small, pretty simple system, right? But assume for a minute this is the class diagram for a system. Where do I need the flexibility? Which areas of the system demands more flexibility than others? It's incredibly difficult to tell at this point. We'll come back to that in just a moment. This is one of the advantages of modularity. Over time, as the complexity of our software system increases, as our software system grows, and we fight against some of the changes that we've made, the complexity increases and our knowledge of the system decreases. However, with modularity, what happens is that there is a slight increase in complexity over time. I recognize that. Modularity is not free. We are introducing new concepts, new ideas into our environment. In fact, modularity attacks the essential complexity associated with software development. The essential complexity talked about by Frederick Brooks in his book, The Mythical Man Month. Brooks talks about accidental complexity. This is the complexity associated with the tools that we use. Accidental complexity can be eliminated. In fact, it's this accidental complexity that has plagued OSGi over the past several years. As the tools get better, that accidental complexity is eliminated. But the essential complexity, the essence of software engineering, the fact that design is difficult and designing software systems is always going to be difficult. So yes, even with modularity, modularity is not a silver bullet. It introduces something additional into our environment. But long term, it is going to allow us to maintain the knowledge of the system that we need to understand it more effectively. I draw an analogy here with test-driven development. A lot of developers that I'd worked with several years ago, not so much anymore, but several years ago, as we began to look at JUnit and unit testing and whether or not we should do TDD, the developers who resisted, the most common complaint from them was that it's going to take me too much time. I'm sure you probably heard this, or maybe you've been the one who, maybe you felt that way at one time. It's going to take me too much time. I don't have time to write unit tests. Well, think about this for a minute. And I like to draw an analogy to accounting practices. One of the best practices associated with accounting is a technique called dual entry bookkeeping, where for every debit I make a corresponding credit so that when I'm finished, the bottom line should zero out. And if it doesn't, then it means somewhere in my debit or somewhere in my credit I've made a mistake. That's essentially what unit testing is. It's like dual entry bookkeeping. I write the code, I write the test, they should reconcile. If they don't, then I've made a mistake somewhere. So when it's time for me to go seek an accountant to help take care of my money, if that accountant looks at me and says, you know what, my services are cheaper than the guy next door because I don't practice dual entry bookkeeping, would it be wise for me to work with that accountant? Probably not. It is a professional practice associated with accounting that they do dual entry bookkeeping, just like unit testing has become to a great extent part of our professional responsibility. So too it is with modularity. The fact that we should be designing these software systems with this modular architecture, and yes, it's going to be a little bit extra work. But the dividends will pay off at some point in the future as I have to go back into this code to try to understand it. Because if there's one thing that I found consistently over time, it's that every time I go to maintain a piece of software, it's typically challenging. Well, the first thing that happens is I pull up the code in my editor and I look at it and I said, who wrote this code? Why is it that all of the code that's written by any other developer is always crap? Have you ever noticed that? Any code that's written by someone else is always crap code, isn't it? And then half the time I realize, oh, wait a minute, I'm the one that wrote that code 6 months ago, 9 months ago. And now I'm trying to understand it. It's that understandability associated with software that's incredibly challenging. Studies have been done that show that 50% of the time associated with software development is spent simply understanding the software system. Other studies have shown that 90% of the cost of a software system is all maintenance, which makes sense. You think about a typical software system that might live 5, 10 years. It takes 12 months to develop, and then it lives on for 9 years, undergoing constant change, constant evolution over that time period. Modularity helps us understand the software system and allows us to maintain that understanding over time. And this is directly related to the concept of surrounding architecture I like to call architecture all the way down. We're going to talk about that here very shortly. So back to my original diagram here. Which area of the system demands the most flexibility? Well, if I don't have a modular software system, it's relatively difficult for me to tell. But if I allocate this functionality to a set of modules, it becomes more apparent that where I really need to focus my design energy, my architectural energy, is on the architectural joints or the seams in my system. It is the relationships that span the modules. Think for a minute, just a show of hands. How many folks here spend time designing class relationships? You know, class structure, object-oriented design. Okay, so I'm assuming a few of you aren't raising your hand because I'm guessing that most of us do, but we got about half. How many people actually spend time on package design? That is your Java package. And not just determining what should go in a package, but also managing package relationships. Okay, so a few, not quite as many. And how many people do the same for your modules, your jar files? Okay, so a few, but even less. And that's typically what I see. As I ask folks these questions, I find that just about everyone spends conscious effort designing their class structures. The behavior of a class, the relationships between classes. A few of us spend time designing package structures, and then even fewer actually focus on the relationships between modules. If I don't focus on packages and modules and relationships between services, identifying the flexible areas of my software system is going to be more difficult. Because quite frankly, as I package these things up, I'll notice that anything inside of a particular module is going to be encapsulated. The design is encapsulated, the logic is encapsulated, and change can be encapsulated. It's the seams in my system where I really need to focus my flexibility. And as I do that, what I quickly discover is that it affects my design in interesting ways. So let's just take a look here at something relatively simple. Couple of visuals here that I want to show. So here's a class structure on the left-hand side. Very, very simple. A customer has a bill. Okay, this class structure happens to be bidirectional. That is, the customer depends on bill and the bill depends on customer. The worst form of coupling that I can have, to have this bidirectional relationship between classes. But how bad is this design? If this design is encapsulated within a single module, yeah, it's still bad, but it's not terrible. But if this design spans modules, then it's bad. Because ultimately, I can't use one without the other. And what's interesting is that when I begin to design modular software, and many of you might be sitting there thinking, you know what, Kirk, you're talking about jar files, designing modules, how we go about packaging our software system. Yeah, that's what I'm talking about. But what's interesting is it really has the ability to affect our design in very, very interesting ways. For instance, if I wanted to get rid of that cyclic relationship, I can apply a technique called demotion, where I demote the reason for that cyclic dependency between the modules to a lower level entity. In this case, I push it down to something called a discount calculator. I have the ability, if I want to escalate the reason for that dependency to a higher level entity. In this case, the payment mediator. And as I do this, you can see how my module structure on the right changes. I can actually, by introducing an abstraction, a couple of abstractions, completely reverse the relationship between the two modules. Prior to this, the customer module was dependent on billing. This time, billing is dependent on customer. In fact, if I want to, I can completely eliminate the relationship between the two modules. In this situation here, customer and billing no longer have a relationship to each other at all. Now, if I weren't focused on designing a modular software system, I would not have much motivation whatsoever to introduce these abstractions that allow me to decouple things in the way that I have here. Think for a minute about how many people here have ever used the java.sql package. No one? I'm sure most of us have. Think about java.sql. What's inside of that package? Java.sql contains nothing but abstractions. Yes, okay, it contains a couple of exceptions and maybe some concrete classes that define some constants, but that's pretty much it. Java.sql contains nothing but abstractions, interfaces or abstract classes. Where do the implementations for Java.sql actually live? They live within our database drivers that we use, which is typically in a completely separate entity somewhere. That is why we have the ability to connect to Oracle and DB2 and all of these different databases. Now, unfortunately, Java.sql and the JDBC drivers associated with, or the database drivers associated with Java are only isolated to a separate package, not a separate module. That's a separate issue we're going to talk about a little bit later. But by separating the interface from the implementation, we give ourselves significant flexibility in the runtime implementation that we can choose. And yet we don't take this approach to design with our own software systems very often. So ultimately, as we begin to modularize our software systems, what we are going to find is that modularity affects our design in some pretty interesting ways. It's more than just how we go about packaging the system. It will have an impact on the abstractions that you create and where you place those abstractions. I've worked with developers where every time they create a concrete class, they create a corresponding interface associated with that class. So I create a person class. By default, I will create an iPerson interface. Maybe some of you have seen this. And then where do you suspect they put that iPerson interface? They put it in the same package as the class itself. That is an example of poor package design. If you put the implementation and the interface in the exact same location, you may as well not create the interface in the first place. Interfaces should be farther away from the classes that implement them and closer to the classes that use them. If you put them in the same location, you are not giving yourself the ability to take advantage of the abstraction that you've created. We're going to see some examples of this a little bit later on. How many people here layer their software system? Presentation, domain, data access. I know that many of us probably do. How do you actually know that you have a layered software system? How do you know that you do? What do you do to enforce, to validate that your software is actually layered? How do you know that some developer has not, within the data access layer of your application, decided to import something in the UI layer? What sort of validation, what sort of enforcement do you have in place to validate that? With modularity, we give ourselves the ability to validate, to put these enforcements, these constraints, these tests in place. So what are the benefits? Well, based on what we've talked about up to this point, reuse. Think about how you go about reusing a piece of software. We really need look no further than the open source community for this. Every time you reuse a piece of software that you download from Apache, you download a jar file. Log4j is a wonderful example. Well, it's a good example. Okay, it's a good example. It allows us to reduce complexity. It allows us to reduce complexity by focusing on specific areas of the system where we need the flexibility. It allows us to ease maintenance because we have the ability to understand our software system more easily. Log4j is actually a pretty good example because think about how reusable Log4j actually is. It's a very reusable piece of software. But every time I reuse Log4j, every time I use Log4j in an application, I always curse at it because I absolutely hate configuring Log4j. I don't like doing that. But what's interesting there is that if I didn't have the ability to configure Log4j, it wouldn't be very reusable. That reuse comes with the cost of use. The same is with our modules that we create. As we create something that is more reusable, it's inherently going to be less usable. So I claim that modularity actually allows us to increase architectural agility. What is agile architecture? Well, we talk a lot, of course, over the past 10 years about agile software development methods, but what is agile architecture? It seems to have there's a few books, not a lot, a few blogs, not a lot, nothing compared to what we can find surrounding agile software development processes. Where do we go to find information about agile architecture? I think there's a pretty serious lack of it, for one. But what is agile architecture? What is architecture? Is architecture a thing that we create? Is it the structure of the system? Or is architecture the process that we go through where we arrive at that structure? I think it's probably at least both. And when we think in terms of agile architecture, are we thinking about the process that we use to develop our architecture? The process that we go through and when we make those decisions? Or are we talking about ultimately the resulting flexibility of the architecture itself? Because one without the other is going to impede architectural agility. I can say as an architect that I am willing to embrace change. I am willing to embrace change. I am going to allow my system to adapt and evolve and for designs to emerge. And yet, if I don't have a system that can accommodate that change, how agile can I ultimately be? I'm sure you've all been in this situation. I open up my Eclipse editor, and I'm going in to change a single line of code, and I am absolutely scared to death that the change I am about to make is going to break the system somewhere. I finally work up the courage to make that change. I make the change, and somewhere over here, unbeknownst to me, something is now broken. And I take a step back and I think, there is no way that the change that I just made could have possibly broken that area of the software. And I think, you know what? It's just too big of a coincidence. And as I dig a little deeper, I discovered this interesting ripple effect associated with the change. And what that's an indication of is it's an indication of the lack of modularity, because with modularity I have the ability to more effectively understand the implication, the ripple effect associated with change. Because of this idea right here. As I package my classes up into modules, modules serve as a higher level view into my software system. And for a complex system with hundreds or if not thousands of classes, I may only have a few dozen modules. And it's going to be much easier for me to understand the relationships between those modules than it is the relationships between all of those classes. And this brings us to the notion of architecture all the way down. We design class relationships. We spend time thinking in terms of class granularity, class cohesion, the relationships between my class structure. Not so many of us spend time doing the same for packages. And even fewer of us spend time doing the same for our software modules. But in doing so, we give ourselves multiple levels of abstraction at which to view the system and from which we can understand the system's architecture. But we not only have to design it from a conceptual standpoint, we also have to do things that validate it and that enforce it. I mentioned earlier, how do we know we have a layered software system? What are we doing to actually prove that we have a layered software system? Later on, we're going to talk about the physical layers pattern, which is the first step towards actually demonstrating, proving, validating, enforcing the layers in our system. And then we're going to challenge the notion of layers altogether. The reuse release equivalence principle. The unit of reuse is the unit of release. Think in terms of what these different entities on the Java platform are good at, what their purpose in life is. Classes are good as a unit of state. That is, they have instance variables associated with them, so on and so forth. They're behavioral. Packages, Java packages are a way to organize classes. They're a unit of composition. We compose classes together, we put them in a package, and this package should have some level of granularity and behavior associated with it. Look at a module. In fact, the only thing on the Java platform that is a unit of intra-process reuse is a module, a package, or a class. And we combine that with the unit of deployment, and that leads us directly to the reuse release equivalence principle. We certainly don't deploy classes, we don't deploy packages, we deploy modules. Unit of deployment, unit of intra-process reuse. It's really the only thing on the Java platform that intersects those two things. So the turtles up there actually are there for a reason. It's a story that was, I find pretty interesting, kind of a funny little story. Bertrand Russell was giving a lecture one time, and he was talking about how the moon orbits around the earth and the earth orbits around the sun. And at the end of the lecture, a little old lady stood up and said that what you told us is rubbish. That everyone knows that the earth is supported on the back of a giant tortoise. And the lecturer, Bertrand Russell, asked the little old lady, well, what is the tortoise standing on? And she said that it's turtles all the way down. And I like to draw an analogy here to architecture, because when we think about architecture, what is our focus? What are we focusing on from an architectural standpoint? Are we focusing on the relationships between services, the service interface? What is architecture that we focus on? Are we focusing on class structure? Are we focused on the big decisions that we make throughout a software project? Is deciding to use Spring an architectural decision? Is deciding to use Hibernate an architectural decision? What are these architectural decisions? And the argument here is that architecture all the way down allows us to bridge the gap that we oftentimes see between architecture and design, that we oftentimes see between the architects and the developers on the team. We've heard of this notion of ivory tower architecture, where the architect in his or her tower throws designs down to the developers who attempt to implement that architecture. And on most software projects, what you typically find is that the architect thinks that the architecture looks like this, But then you go ask the developer and they say, oh no, we couldn't do it that way because it didn't work. And they've just gone off and done their own thing. Well, what constraints, what enforcements can we put in place? And I'm not, when I say enforce and constraints, I don't mean that the architecture the architect should put these things in place to force the developers to do things a certain way. But it can serve as a way to communicate. It can serve as a way to open up those channels of communication. And by introducing modularity into the mix, it gives us another level of abstraction at which we can focus. And we actually now have the ability to validate our architecture. So this brings us to the modularity patterns. There's 18 patterns divided into roughly five different categories. I should probably know that, right? 5 different categories. The first are the base patterns. These kind of lay the premise for designing modular systems. Next are the dependency patterns. The fact that modular relationships should be acyclic. We should levelize modules. We'll talk about that a little bit later. Module relationships should not violate the conceptual layers. Let's pick this one for a moment. Because earlier I asked you how many of you design layered software systems. And a lot of you raised your hands. We have typical layers: presentation, business logic, data access. Those are the traditional layers of a system. But in many ways, those are only conceptual layers. How do you know you have a layered system? If you truly have a layered software system, then what you should be able to do is you should be able to compile your data access layer without the business object or the presentation layer in the compile time class path, in the build class path. And then you should be able to compile your business object layer with only the data access layer in the build class path and up to the UI layer. If you can't do that, then you don't have a layered software system. Sometimes in software development, I think we oftentimes just do things because that is the way we've been taught to do it, and nobody has actually taken a step back and challenged, why am I doing it this way? Why am I continuing to layer my software system conceptually only, but not actually physically? Why not separate these layers out into physical modules, physical units of deployment? Why do we layer our software system? We layer our software system, at least I've been told, because one, we want to isolate change to a specific layer. So that if a business rule changes, I can go only into the domain layer and change that rule. Or I have the ability to change the UI layer. I can change the user interface without changing my business object or domain or data access layer. But then, even if I change something in a specific layer, ultimately what I do is I take this, I typically recompile the whole system and redeploy everything. So I've confined change to a single layer. Then I take everything and I recompile and redeploy it. Everything. So have I really isolated anything? How easy is it for you today to take an existing software system that you've developed and actually build a new UI on top of that system? How easy is it for us to do that? Well, in many situations, what it involves is trying to figure out what I'm going to pull out and what I'm going to put in and where I need to do it. Even though I have these supposedly individual layers associated with my system, they're only conceptual in nature, and I oftentimes don't do anything to actually prove, to validate, to enforce the layers. Another interesting aspect. A lot of times, the relationships between layers, whether it be from UI to domain or from domain to data access, is actually dependent upon concrete classes. So if I have a class in my UI layer that is dependent on a concrete class in my domain layer, and my domain layer is dependent on a concrete class in my data access layer, then I don't have the ability to substitute new layers in for existing ones. I can't rip out my data access layer and replace it with something else. Which begs the notion, how valuable is it to actually layer our applications? How valuable is it to actually layer these applications only conceptually, to not actually physically layer them? And then the conceptual layers that I have in place are all tightly coupled with class relationships between several concrete classes that span the layers. I mean, in theory, if you think about what the most flexible system architecture would look like, software architecture would look like, it would be where we had modules, software modules, with concrete classes in them, where those modules pointed only to other modules with abstractions in them. It wouldn't represent a layered system. It would more or less look like a big circle of modules on the outside pointing to a bunch of modules with abstractions in the middle. That would be much more flexible, because I could rip and replace any of the modules at will, as I needed to. Usability patterns, published interface. In Java today, I actually don't have the ability to implement this notion of a published interface. That is, what are the behaviors of a module and how do I expose those behaviors via an interface? Some of you may have, at some point in time, browsed through the JavaDoc documentation and noticed that at some point there's a comment that says, this class or this method should not be called by your code. It should only be used internally by the JDK itself. That is a problem that is brought on because of the lack of modularity. I have no way to encapsulate anything on the Java platform. Okay, yes, I can create a private method. But any class that I create, is essentially global once it's been added to my class path. I can't encapsulate anything. So even if I put these wonderful abstractions in place, these interfaces, and I bind everything to interfaces and avoid concrete coupling, all it takes is one developer to come along and do a downcast to a concrete class to compromise the flexibility that I put in place. And there is absolutely no way that I can enforce or prevent that from happening. Yes, I know that you can have this notion of public or private classes within a package by not putting the public identifier in front of the class name. But that only really gets us partway there. That only gets us partway there because I can still use class.forename or a dependency injection framework like Spring to dynamically create that class. Spring can just reach inside of there and create that thing anyways. Java doesn't enforce that type visibility for me. So it's actually quite difficult to create a published interface on the Java platform without a module system. Extensibility patterns, abstract modules. This was my point when I was talking about physical layers. Depend upon the abstract elements of a module. Separate abstractions. Place abstractions in the classes that implement them in separate modules. The ultimate in flexibility. Think in terms of how modules are the unit of reuse, the unit of release. And if I put abstractions in the implementations in completely separate modules, I've given myself a world of flexibility surrounding the opportunity to replace the implementation with something else without affecting any other part of my system. And then some utility patterns. So now what I'm going to do is I'm going to switch gears a little bit, and we're going to get a little bit more into the code, and we're going to take a look at what we can do, how we can use these patterns to develop a modular software system. So I'm going to jump over to, I'm going to show you this system, the initial version of this system, where I spend time designing the class structure and have a decent structure in place. Debatable, I guess. I think it's decent. And then I'm going to just package this up and deploy it as a WAR file. So what I've just done is I built the software system. And there is now a WAR file. And again, all of this code is available on that GitHub repository, the billpay.war file, and I'm going to deploy that to Glassfish. And then I'm going to show it to you to prove that it actually works. And I'm also going to point out that I am not a user interface designer. So if you need a UI expert, I'm probably not the one that you want to look for. Anyway, so this is an application that allows me to pay bills. It's actually derived from a real-world application that I worked on at one point, where we would take in these bills that we had to pay, but before we paid them, we would send it through this repricing routine where we would apply some form of a discount to that bill based on an arrangement that we had with the organization that was submitting the bill. So I'm going to do a search for a customer. I'm going to get back Sue Smith, and she has 5 bills. I'm going to choose one of those bills. I'm going to audit, which applies the discount, and then I am going to pay it, which actually pays that amount. So nothing too fancy here, very, very simple. But we're going to take this thing because the initial version of this system was designed as a very, very monolithic application. That is, I spent some time designing a relatively flexible class structure where in the red I have my presentation layer, and in the blue I have my domain layer. So I've spent some time separating these things out, but only conceptually. And then I take this during the compilation step, and I package everything into a WAR file. So everything is deployed as part of this single WAR file. And today, notice right now, that there are some bidirectional relationships here, like between the bill and this class that I call the audit facade, and this class that I call the payment. Okay, so those are some bidirectional relationships that exist there. So that's the initial class model. This system actually uses struts, at least for now it does. And if I conceptually layer my software, then I claim I'm not really taking advantage of what layering provides for me. Think about some of the systems that you've developed over the past several years. How many people here have developed a system using struts? And how many people here at some point in time have decided that, you know what? Struts is a framework from a bygone era. I no longer want to use struts. But the issue that I have is that taking this piece of software that I've developed and trying to refactor it and remove struts from the mix is incredibly challenging. How do I rip that web framework out and replace it with something else? Well, as we go through these refactorings, what we're ultimately going to see is that that becomes an incredibly easy thing to do. And not only is that easy to do, but as we introduce some of the runtime benefits of modularity, I can actually just deploy new functionality into my runtime environment without really affecting anything else. So, but this is what I've got initially, just this bill pay WAR file. Everything is packaged as part of this single unit of deployment. And then I've got the struts in the webenv directory. And as I mentioned, this is a system for paying bills. In the real world variant of this system had to integrate with some third-party auditing software and a legacy financial system that was written using COBOL and CICS, which as Java developers, we know that's a joy to work with. So this was a relatively typical large enterprise software system with the typical complexities that we might face. So the first thing that I wanted to do is to separate this out into physical layers. Step one. Now, as we walk through these examples, I want to point something very, very important out. And that is, you have to keep in mind that this system has been simplified for the purposes of demonstration. As a result of that, many of the modules that we'll see here and that we'll talk about tend to only have a couple of three, maybe a few classes at most inside of them. I do not advocate that in the real world. In the real world, when we're designing modular software, I would expect modules to have more than just a few classes inside of them. They may have 50, they may have 100. It depends on what the right unit of what the right level of granularity is and the right level of cohesion. But don't walk away from this and say, oh yes, I need modules, my modules can only have a couple of three classes inside of them. Don't take that back with you. Instead, focus more on how the behavior of the application drives the resulting structure. So the physical layers pattern says that the module relationship should not violate the conceptual layers. Now, one of the reasons why I needed to do this is because this application actually had to run in batch mode. So it had to run not only on an app server in a servlet container, but it also had to run directly atop the JVM. And when it ran atop the JVM, I didn't want a user interface on top of it. Instead, what I was doing is I was accepting incoming electronic bills that I would parse and send through the payment process. So I actually had the need to separate the user interface from the rest of the application. So as this need arose, and I tried to do this, because I thought I had a layered software system, which meant that it was going to be easy for me to separate this thing out into the physical layers. I thought I had a presentation layer. I thought I had a domain layer. I thought I had a data access layer. But it was all conceptual. And when I actually tried to physically separate these out and build the domain layer separate from the presentation so that I could deploy it in batch mode, what I discovered were all of these dependencies that had crept into the domain layer that none of us knew anything about. and that really prevented me from separating that domain functionality out into a separate layer so that I could reuse it in my batch application. And it actually took a considerable amount of time to refactor that domain layer to remove those dependencies. And that's why I say, for many of us, we think we have a layered system, but it's layered conceptually, and if we don't do something to enforce it, we can't say for certain that we have a layered system. I also find it quite interesting that just about all of us decide to layer the system, and we operate under the assumption that we do have a layered system, but we don't do anything to enforce it. At that point, what's the point of even devoting any energy into a design practice if we're not actually going to validate that the result is what we set out to achieve? We may as well not do it at all. So, I've got my physical layers at this point now, and actually, if I show you that, in terms of the first refactoring, and I build that thing, what we're actually going to see here is that I now have in my bin directory this build.jar, and I take that module and I basically include it in the WAR file. Okay. Okay. So now I can take that module and I can reuse it anywhere that I need to. Next up is abstract modules. Depend upon the abstract elements of a module. Ultimately, what I'm saying here is that the relationships between modules, remember the seams in the system, the architectural joints, the seams in the system should depend upon abstractions and not upon the concrete elements. If I'm dependent upon the concrete elements, I lose a lot of flexibility surrounding how I can manipulate and massage the implementation at runtime. So the need here was that currently my bill class and my audit facade class are tightly coupled. And if I went and I took a look at this code, I can see that the audit method for bill actually creates the instance of audit facade, and then it passes itself into that audit facade. And if I looked at the audit facade, I would see exactly what I'm talking about here. It accepts an instance of bill, the worst form of coupling, a bidirectional relationship here. So what I ultimately have to do is break this relationship apart. Pretty simple to do. I introduce an abstraction. Nothing fancy going on here yet. I introduce an abstraction that bill is coupled to, so that what I end up with is the ability to separate these two things out into separate modules. It's just that at this point I still have a cyclic relationship, which brings me to the third refactoring, which is module relationship should be acyclic. The acyclic modules pattern. I want to try to avoid that bidirectional relationship between classes. That's the problem that I now need to solve, and I'm going to do it by introducing an auditable interface. This auditable interface is going to allow me to pass the bill into the audit facade as this auditable data type. And if I take a look at this, you can see that bill now implements auditable. Everything else is still pretty much the same. If I go take a look at my audit facade, it now accepts an auditable instead of the bill. So I have broken apart that bidirectional relationship by introducing the abstraction. But what's important to point out here is, where does that auditable interface live? If I put auditable in the same package or the same module as the bill, I haven't broken the bidirectional relationship between my modules. So what's interesting is that I can have an inherently flexible class design, but if I don't focus on how I organize my packages and I don't focus on how I organize my modules, the resulting physical structure of my system will not possess the same flexibility as the conceptual structure, the class structure. I could put all of these in the same package. I could put auditable in the bill package, and I would still have the same flexibility as what I see here. I've still decoupled bill from the auditable implementation. I've still decoupled the two. And now I have tremendous flexibility from a class standpoint with how I work with different audit facades. The basics of dynamic binding, 00101. But if I don't separate them out into different, if I don't allocate them to the right modules, I don't realize the full advantages of modularity. Or I don't realize the full advantages of that structure. So the key here is to make sure I consciously think about where I put that auditable interface, and it needs to go farther away from the bill and closer to the thing that uses it, which is the audit facade. So it goes in the audit jar. And as I do this, what I notice is, one, my bidirectional relationship, the cyclic relationship between modules, is now broken. I also have a few more modules that introduces a bit more flexibility into my system. Now, how does it help aid understanding? I know that if I change something in the bill module, that the ripple effect of change has to be confined to anything that is dependent upon it. Prior to my refactoring, if I were to change the bill class, it could have affected just about anything in my system, because one, of the bidirectional relationship, and two, because I didn't have a modular system. So I didn't know what the ripple effect of change was going to be. Here I confine it, and I have that mental visual understanding of where the change is going to be constrained to. Excuse me. So let's go take a look at this one. About time for a break. So let's take a look at refactoring 3. Thank you. Now, a few things here. First, the build took a little bit longer. You may have noticed that as it scrolled down. I did a couple of things at this point. One, you'll notice that I now have more modules, for one thing. But another thing is that I've changed my build script. I've changed my build script so that I only compile what is absolutely needed, because I do have a unidirectional relationships, acyclic relationships between all of my modules. So when I compile audit, I know that audit didn't depend on anything else. And when I compile bill, I know that bill is dependent upon audit. And we'll see that down here when here's the bill compile. So I include in the bill class path the audit and the financial modules that I built. Now, Would I put all of this in a single build script in the real world? Probably not. I might separate it out, structure it a little bit differently. The point here, though, is there are several advantages to this. Not just today, but also moving forward. First advantage is that I want to enforce the relationships between my modules. I do not want that audit module dependent on anything else. And by compiling it with only what it absolutely needs in its class path, if a developer went in and decided they were going to import something that they shouldn't be importing, the build would fail. So I actually enforce the layers of my system using the build script, using a levelized build. The layers are actually enforced. In addition to that, as different areas of the system begin to stabilize over time, and this has happened on every software system that I've developed, different areas of the system are going to stabilize at different rates over time. The code that I develop in the first few months of a project probably stabilize as I move on to adding code 12 to 15 months into the project. And as that happens, instead of building this as one huge system, which is ultimately going to slow the build down, I can separate these out into smaller builds and only build what's needed as it changes. So I am only going to build the modules that actually changed. So I might have 4 or 5 different builds set up as part of an individual project to build the respective modules, and each of those builds pull in what it needs from the other modules, which is going to allow me to keep build times relatively fast, instead of just building everything as one big single application. I also incorporate into this a utility called Jar Analyzer that I'm actually going to run here quickly. Because it's a visualization utility that allows me to see the relationships between my modules. And this is what I have at this point. I've got my bill module that's dependent on financial and is dependent on audit. So that's actually what I showed, nothing significant here. What I like about this, though, is that it's real time. It uses bytecode analysis to look at the jar files, the modules in a particular directory. I excluded the test modules from the output. Looks at the modules in a directory, analyzes the relationships, and uses graph viz to create a visualization of those modules. We'll see more of that a little bit later as we incorporate additional modules into our build, or as we separate this out into additional modules. Separate abstractions from the classes that realize them. Well, I just said we want to put the interfaces and the implementations farther away from each other, but my audit facade implementation and interface are in the same module, which is going to cause problems when it comes time to replace the audit facade with something new. Now, where is all of this headed? Where all of this is headed is to the point where I have the ability to rip and replace the guts of my system, or to rip and replace the UI of my system with relative ease. And I'm going to show examples of that in a little bit later. The need here, the driving force behind this, was that the way that we adjusted bills in this organization was going to change 3 months after we went live with the system. So we need, the reason being that we had a vendor contract that expired in 6 months, and we knew that we were going to be choosing another vendor. And so we knew that we needed to rip and replace this functionality 3 months into our deploy to production. So we needed the flexibility to be able to do this. If I left the implementation and the interface in the same module, it meant ripping out the implementation would have also ripped out the interface. So I need to separate these. I can't put audit facade 2 in the audit jar because I want to get rid of the original audit facade. Separate abstraction says, well, let's put these things into separate modules altogether. Let's separate them out. Let's create an interface-only module that serves as the contract between the provider and the consumer and the implementation. So that audit spec module contains only the interfaces, and the 2 different implementations live in audit 1 and audit 2. And if I go take a look at this, now I'm not deploying each of these, but keep in mind that these are refactorings that aren't really affecting the system, and so the system functions the same each time through. The abstractions that I'm introducing to decouple the modules don't have any behavioral change on what the application does. It is doing what the application does. It is doing the same thing each time through. If I take a look at this, what you'll see is that progressively I'm getting more and more modules included. What's also interesting here is because I do have these modules, I am creating a corresponding test module that tests the functionality of each individual module. So I've got a financial module, I've got a financial test module, I've got a bill module, I've got a bill test. So there's test modules associated with each of these modules that essentially test that module in isolation. Let me go take a quick peek at the build script to see what I call the target here. Or maybe I don't have it in there. Later. We'll get back to the visual output a little bit later. I didn't include it as part of that build script. So a couple of easy refactorings to finish up here. One, where do the exceptions go? The exceptions need to go close to the interfaces that throw them. If I don't put the exceptions close to the interface that throws them, it's going to create a dependency on some other module that I do not want. So it needs to go close to the interfaces. Independent deployment. What happens if I want to use that bill module without the legacy financial stuff? How do I remove that dependency altogether? Well, currently this is the structure where I have a bill that calls a payment, passes itself in as a payable. That brings me to a new structure to completely decouple the relationship between the bill and the financial module. I have the ability to do that. Now, I introduced some new abstractions and a bill pay adapter to pull this off. The only reason these abstractions exist and these new classes exist is to allow me to decouple and to massage, to manipulate the relationships between my modules. So before, whereas the bill passed itself into the payment as a payable interface, I've applied a technique called escalation, where I escalate that dependency up to the bill pay adapter. So now the bill pay adapter implements payable, and it has a reference to the bill to get what it needs, and the bill pay adapter passes itself into the payment as a payable. The payment can then call back on the bill pay adapter to get what it needs. This completely eliminates the relationship between my bill module and my financial module, because I introduce a new module called bill pay that encapsulates this relationship. I have essentially escalated it up to a higher level entity. I'm going to show the final one here before we do the build to show the final structure. And then the final one is, now that I've got these implementations, these interfaces, something that we've kind of ignored or glossed over is, how do I actually create the implementations? I can't use the new keyword, we know that. And so how do I create the implementations? I introduce a factory. Where does the factory go? I'm going to put it into that bill pay module so that the bill pay module actually creates the appropriate implementation. And a more flexible approach, of course, would be to use something like dependency injection, which is ultimately what we do when we show this example a little bit later in the OSGi environment. But for now, I am going to run this thing. So it builds the system. Here are my modules with a bunch of test modules associated with them. If I look at that visual now, this is the relationship between all of the modules, which is ultimately the same as what I was showing in the presentation. It's just this is generated from the build directly. And as you can see here, everything essentially points to this audit spec, which contains only the interfaces, and nothing really depends on anything else, which offers me a tremendous amount of flexibility, because now I can basically take that bill module and I can rip and replace any level in this system that I want to. It also allows me to change things relatively independently. I know if something in the Audit 2 module changes, I can change that, and I can compile it separate from anything else. I only need to compile that one thing. I don't need to compile anything else in the rest of my system, and I can simply redeploy that single module. Now, I could deploy this system if I wanted to, and again, because I don't yet have a runtime environment for modules, if I deployed this system, I still don't have the runtime benefits of modularity. So I said that I can effectively take the audit modules and replace them with something else. Because the UI piece is separated out, I can pretty easily now build a new UI on top of this thing. But if I do that, I've got to package everything up into a WAR file and redeploy it. I have to deploy it as an application. But I can easily do it, and modularity has given me that flexibility. It's provided that benefit. After we take a short break here and I bring this under the control of OSGi, we're going to introduce a whole world of flexibility that we didn't have even with just modularizing our application. With some of the things that we can do here. But first, I do want to take a break. Let's take a 15-minute break, and it is 4 o'clock in the morning right now. So let's get back at 4:15. How's that?